Good morning, my name is Johny Matar from the Lebanese University. Today, I will be presenting the paper entitled Impact of Eigensolvers on Spectral Clustering. This research is done with my co-authors, Hicham and Khoury from the Lebanese University, Jean-claude Charr and Christophe Guyeux from Université Bourgogne Franche-Comté. This presentation consists of 5 sections. In the first section, I will introduce the spectral clustering technique and the target of this research. In the second section, a brief explanation of the eigensolving problem will be presented, along with some existing libraries that implement algorithms for solving the eigen problem. Our experimental protocol is presented in the third section, followed by our results and findings in the fourth section, before concluding this presentation. So what is the spectral clustering technique and what is it used for? The spectral clustering technique can be applied for the analysis of data and graphs. It has a wide variety of application fields, including the detection of intrusions in computer networks, for example, the analysis of the maps and structures of power grids, the analysis of text documents, pictures, and it was also introduced lately as an efficient technique for the analysis of biological sequences. But how is the spectral technique applied? The spectral technique consists of the following computation pipeline. First, we need an adjacency matrix. This adjacency matrix consists of a pairwise similarity matrix among the elements of the targeted data. This matrix contains real numerical values between 0 and 1 for expressing the extent of similarity among each pair of elements. Moreover, this matrix is symmetrical by nature because the similarity between 2 elements I and j, for example, is the same as saying the similarity between j and I. The next step, or the next computational step in this pipeline, is the computation of the normalized Laplacian form of this matrix before extracting the spectrum. The spectrum is formed by the transpose of the matrix holding the leading eigenvectors of the normalized Laplacian matrix that was previously computed. And this spectrum presents the original data as points in a space that has a dimension n. By taking each pair of coordinates of the components in this space, we can visualize the repartition of the data in several 2-dimensional spaces, as illustrated in the figure in the lower right position of this slide. This helps in the choice of the clustering technique that should be adequately chosen for the last step of this pipeline. For example, the k-means technique successfully detects spherical shaped clusters, while the Gaussian mixture model is able to detect elliptical shapes as illustrated in the adjacent figure. Therefore, the choice of this technique is crucial based on the visualized repartition of the points in the plane. In this computation pipeline, the implementation of the eigensolver influences the 2 aspects that are the subject of this study. The first aspect is the speed of computation of the spectrum, while the second aspect is the accuracy of its values that can affect the accuracy of the final clustering results of this technique. Let's now define this eigensolving problem. Indeed, in its general form, it consists of an algorithm for computing the solutions of the following mathematical equation: A scalar V equals lambda scalar V, where A is a square matrix, V is an eigenvalue, and lambda is an eigenvector. This equation can be simplified under the form of A minus lambda I equals 0, where I is the identity matrix. From this equation, we can obtain a system of equations from which we can compute the eigenvalues before computing their corresponding eigenvectors. This computation of this problem is done via iterative algorithm that has undergone major improvements in the literature, especially by proposing and using parallel schemes for its acceleration. Indeed, several libraries include an implementation for solving the eigen problem. On one hand, some of these libraries implement an algorithm for solving the general eigen problem that can involve the existence of imaginary eigenvalues and imaginary elements in the eigenvectors. Laplac, Armadillo, and Eigen are few examples of C++ libraries implementing the general eigensolving algorithm. Here, I would like to highlight that Laplac is built on the top of another library called the BLAS that is an older Fortran library. While Armadillo is also not completely independent, it is also built on the top of Laplac and uses many functions of this library. Conversely, Eigen is a more recent and independent library that was proved faster than its predecessors in one of the state-of-the-art comparative studies. On the other hand, other libraries include other algorithms such as Jacobi's algorithm that can be applied in a special case where all the values are real. One of the mathematically proven special cases that has purely real values is the eigen solution of a real and symmetrical matrix. Back to the spectral clustering technique, we recall that this condition applies to the adjacency matrix and its transformation. We mean by its transformation the computation of the normalized Laplacian form. Therefore, both the general eigensolving algorithm and Jacobi's algorithm can be applied in the spectral clustering pipeline. In order to assess the difference in the computation between the previously introduced algorithm and their impact on the final clustering results, we select the eigen library as an implementation of the general eigensolving algorithm and an online publicly available implementation of the algorithm of Jacobi. For the computation speed assessment, we select 3 dense matrices of different sizes. These matrices are chosen to be dense in order to increase the computation complexity of their eigenvectors. This computation is also done several times on each matrix in order to avoid any abnormalities in the recorded time that can be caused by another running background process. Next, for the assessment of the impact on the clustering accuracy, we select 3 biological data sets for our experiments. The reference clustering of these data sets was deduced by building their corresponding phylogenetic trees as illustrated in the adjacent figure. Then the clustering accuracy was assessed by computing the adjusted rand index, that is an external clustering validation index that ranges between 0 and 1, where the score of 0 represents a completely different clustering, while the result of 1 shows a matching clustering with the reference 1. The results of our experiments were as follows. The implementation of Jacobi's algorithm computes the spectrum much faster than the implementation of the general algorithm. This result is not observed indeed, because solving a special case is expected to be more lightweight than solving a general case. But the difference between the recorded time revealed impressing, since Jacobi's algorithm performed at least 28 times faster than the general algorithm. Accuracy-wise, the results were also in the favor of Jacobi's algorithm, where the clusterings scored a slightly higher adjusted rand index for 2 out of the 3 experiments, as illustrated in the following table. Therefore, we can conclude that the use of an implementation of Jacobi's algorithm is potentially more adapted for computing the spectrum for the spectral clustering. As a continuity to this research, we intend to extend our experiments over other types of data in order to further prove our conclusion. Moreover, investigating further possible acceleration for the eigensolvers can also accelerate the spectral clustering technique, that is a computation-hungry technique. Finally, it could be interesting to find a novel and more lightweight algorithm for computing a spectral embedding without going through the eigen problem. Thank you for your attention.